Welcome to The Explainer. Today, we're diving into something that's totally transforming our world, machine learning. And what's wild is that to understand it, we're going to see how the whole quest to build these smart machines, well, it started by looking right in the mirror.
So, can a machine really learn like a human? I mean, that's the big question, right? It's what kicked this whole thing off. And to even begin to answer it, you've got to look at how we learn. Think about it. We're basically learning machines from the second we're born, just soaking everything up.
So it makes total sense that the folks who first started thinking about this stuff, the real pioneers, they weren't just computer scientists. They looked straight to psychology and neuroscience for ideas. They weren't just trying to program a computer. They were trying to, bottle the lightning of learning itself. And you can kind of trace this journey in a few big steps. First, way back, it was all about behaviorism. Think Pavlov's dogs, right? Stimulus, response, reward. That idea of trial and error became a huge part of machine learning. Then, in the 50s, things got a little more cognitive. We started thinking about how humans categorize things. Learning what a cat is by seeing a bunch of examples. That's the bedrock of classification today. And finally, starting in the 60s, we got even more direct and started trying to build things that look and act like the neurons in our own brains. And that led us straight to neural networks and deep learning.
Okay, so that's the history. But how do you actually define machine learning? Well, lucky for us, a guy named Tom Mitchell came up with a really clean definition back in '97 that everyone still uses. And it sounds kind of academic, but when you break it down, it's super simple. It really just comes down to three key things.
Let's use a real-world example here. The task, or T, could be something huge, like predicting if a patient is going to develop Alzheimer's. The experience, or E, is the data you feed the machine, thousands of brain scans, genetic info, clinical notes. And the performance, P, is just asking, how good is it at making that prediction? So the whole idea is that the machine learns when its performance on the task gets better and better the more experience or data you give it. More data, better performance. That's really it. That's the magic.
But here's something that's really, really important to get. This is not just, statistics on steroids. It's a fundamental shift in how we approach problems. It's a whole new way of thinking, and that's especially true in a field like medicine.
And this slide just lays it out perfectly. Look, traditional stats is all about explanation. It's great at looking at a big group of people and saying, okay, on average, patients with this condition have this trait. It tells you why something might be happening at a group level. But machine learning, it's all about prediction for the individual. It flips the question from why does this group have this trait to what is going to happen to this one person. That is a game changer.
And that is why this is such a big deal. Think about it. For so long, there's been this gap between what we find in a huge research study and what a doctor can do for you, personally, when you're sitting in their office. This power of individual prediction is what's closing that gap. It's literally the engine driving us towards truly personalized medicine.
All right, so we get the what and the why. Now, let's dig into the how. How does a machine actually learn? Turns out there are a few different styles or flavors of learning. Okay, here are the big four. You've got supervised, unsupervised, semi-supervised, and reinforcement learning. They're all super interesting and powerful in their own right, but honestly, the one you see the most, especially in things like medical research, is by far supervised learning. So let's zoom in on that one.
So, why supervised? Well, it's pretty literal. You're acting like a teacher for the algorithm. You give it a bunch of data that already has the correct answers labeled. It's like giving a student a practice test with an answer key. The algorithm takes a guess, you show it the right answer, it sees how far off it was, and it adjusts its strategy. It does this thousands, even millions of times, until it gets really, really good at predicting the right answer on its own.
And even within supervised learning, you're usually doing one of two things. First, there's classification. This is all about putting things into buckets, or categories. Think, is this email spam or not spam? Or, does this patient have the disease or not? It's a yes or no, A-B kind of question. The other type is regression. This is when you're trying to predict an actual number, a continuous value. Like, what will the temperature be tomorrow? Or what will this person's symptom score be in 2 years? So just remember, classification is for categories, regression is for numbers.
Okay, we've gone from the human mind all the way to the different styles of machine learning. So if there's one single idea, one ultimate goal that ties all of this together, what is it? What's the whole point?
It is this one word: generalization.
Look, it's easy to build a model that looks brilliant on the data you trained it on. That's like memorizing the answers for a test, but that's not learning. The real test, the only thing that actually matters, is how well that model performs on brand new data it has never, ever seen before. Can it generalize what it learned to the real world? That is everything.
And that's what's so profound here. This power to generalize, to predict. It fundamentally shifts us from just reacting to problems after they happen to actually getting ahead of them, to anticipating them. So as we get better and better at building these crystal balls, really, it leaves us with a pretty big question. If we can train a machine to see the future of an illness in a brain scan, what should we ask it to predict next?